In this video, I'm going to talk about a very interesting and important topic in statistics, and that's correlation and regression, specifically linear regression. Now, there's sort of two components to this topic that are really important in statistics, and that is the correlation part, and that's determining if there is a relationship between two things. And then once we determine that there is a correlation or there is a relationship, so this word correlation sort of synonymous with relationship, if there is a correlation, then can we use that data that has already been collected, that it's already happened, to predict things that haven't happened yet? And that's the linear regression portion. So I'm going to talk about correlation first and then linear regression. So let's start off talking about what the data looks like visually. So we have two pairs of data, and they're matched up. Okay? So normally we have two pieces of information coming from one subject, or one thing. It could be one person or one year, and so those two pieces of information, they can be plotted as a point, as an XY point. And once we plot all of the pairs of data, we call that a scatter plot. And a scatter plot, so this is a scatter plot. It's basically just a bunch of individual points where each point is a pair of data values, an X and a Y. We call the X the explanatory variable and Y the response variable. And once we plot all of those, we can determine if there's a relationship. And so determining whether or not there's a relationship comes down to, do we see a pattern in this graph? Do those points follow a pattern? In this particular graph, I would say no, there's no inherent pattern there. So the correlation, it's a measure of the linear relationship between two quantitative variables. We can't talk about correlation with categorical or qualitative data. As the strength of that relationship decreases, we move from a perfect to a strong and moderate, weak to no correlation. So basically, there's two. If there is a relationship, there's two possible scenarios. When the value of one quantity goes up, the other one also goes up. In that case, we say there's a positive correlation. And if one variable goes up, the value of the other variable goes down, we say there's a negative correlation. So a positive correlation may be something like, as the number of hours you study goes up, the average test grade should go up. And a negative correlation might be something like, as the size or the weight of a car goes up, the gas mileage goes down. And so those are examples of correlations, one positive, one negative. Now our goal is to find a mathematical equation that best fits the data. Now in this case, here's two scatter diagrams or two scatter plots with no linear correlation. So the key word here is linear. In this topic, we're talking about strictly, is there or is there not a straight line pattern? Or do those points follow a straight line? So in A, no, they follow this sort of like a parabola sort of shape. And on the right, in B, it looks like there's no pattern whatsoever. Now, if there's a linear correlation, then the points on the graph should follow a straight line pattern. And so here's some examples of linear correlation. So if you in A, it looks like these points are following sort of the same general direction. As the X values go up, the Y values go up. And in B, they're following this negative correlation. As the X values go up, the Y values go down. So a perfect linear correlation means the points fall on a perfectly straight line. And this usually does not happen in real life, in practice. An example of a perfect linear correlation, something you should all be very familiar with, is if you go to the store. Let's say you go to the supermarket, and let's say you buy, I don't know, a quart of orange juice, so we say quarts, and the price you pay. Well, let's say 1 quart costs $3. All right, well, if you buy 2 of them, you're going to pay $6. If you buy 3 of them, you're going to pay $9. If you buy 4 of them, you're going to pay $12, and so on. So this is an example. So like price per item is an example of a perfect linear correlation. So we're gonna examine situations where it's not very interesting if there's the perfect linear correlation. So we're going to examine situations where there is some moderate to strong correlation. Now, the way to quantify this, the descriptive measure to sort of describe how strong that relationship is, or that correlation is called the correlation coefficient. And so just like the other descriptive statistics that we've talked about, there is one symbol for the sample correlation coefficient and one symbol for the population correlation coefficient. So lowercase r is the symbol for the sample correlation coefficient, and the lowercase Greek letter rho is the symbol for the population correlation coefficient. And so when the value of r is close to +1 or -1, we say there is a linear correlation or a linear relationship. So basically, if those points are tending towards a straight line, or sort of grouped close to a straight line, if the slope of that line is positive, then the correlation coefficient is positive. And if the slope of that line is negative, the correlation coefficient is negative. So, as I said, lowercase r is the sample correlation coefficient, and it's computed from a random sample of values coming from some population. And rho is the population correlation coefficient. And again, this is the only way to calculate rho is to include every single possible data value in your population in the calculation, which we don't normally do. What we normally do is we calculate this one, the sample correlation coefficient. Now, a couple of things about the correlation coefficient. One, it has no units. It's just a descriptive measure, and it's some number between -1 and +1. The closer it is to -1 or the closer it is to +1, the stronger the relationship. And if the correlation coefficient is 0 or close to 0, it indicates that there's no linear relationship. So we're calculating this based on two sets of data. We call them the x values and the y values, and it doesn't matter which one is which. If we switch the x's and the y's, and the x's become the y's and the y's become the x's, it doesn't change the value of r. All right, so calculating the correlation coefficient could be very time-consuming, very cumbersome. So here's the general formula for the correlation coefficient. You can see this is not a nice looking formula if you want to do this out by hand. There's also an equivalent formula which uses the standard deviations, which means you have to calculate the standard deviations before you actually calculate the correlation coefficient. My recommendation is to use Excel. I mean, it's so much faster. It takes a 15-minute problem and turns it into a 15-second problem. Okay, and the Excel function for the correlation coefficient is CORREL. And more on this later on in these notes, and I have other videos where I actually work through calculating the correlation coefficient using Excel. So, and if you watch those videos, you'll see how quick and easy it is using Excel. And so, let me go back a slide. So all of these individual components in the formula, let's say if you were, for some reason, if you were to do this out by hand with paper and pencil and a handheld calculator, even a graphing calculator, it's going to take you very long to do. And so you have these summations, the summation of xy, the summation of x, the summation of y, the summation of x squared, the summation of y squared, and so on. The individual components of this formula, well, they're given here. So there's 6 components to that formula. There's the there's 5 components to that formula. There's the number of values. There's the sum of the individual values. There's the sum of the squares of the values. There's the squared sum of the values. And there's the sum of the products of those values. So, for example, so let's look at a specific example. If you were to calculate the correlation coefficient using this formula, you would first start with some data. So if we want to analyze, is there a relationship between the height of a tree and the diameter of the trunk? Yeah, well, it sounds like you would think that if there's a thicker trunk, the tree would be taller. So it seems like there should be a relationship there. So the first thing you do is you start with the data. So in this case, we have 8 pairs of values. So 8 trees. And for each of those 8 trees, we have the trunk diameter. It's probably measured in inches. And the height of the tree, that's probably measured in feet. And so first, we have to calculate each of these 3 values. And once we calculate those values, we add them up. So we take, for example, let me go back a slide. So this first value, xy, would be 35 times 8. And then this value would be y squared, so 35 squared. And this value, x squared, would be 8 squared. And so for each pair of values, we calculate each of those 3 quantities, and then we add them up. And so once we've added them up, so we have these 8 values here. Let me once we have these 8 values here, we add them up. Then we add up the y squares, we add up the x squares. We have the sum of the x's, the sum of the y's. And because there's 8 values, we would say n is equal to 8. So 1, 2, 3, 4, 5, 6. These values would be plugged into the formula for the correlation coefficient. And that's right here. And then as long as you don't make any mistakes, you should get some number between -1 and +1. In this case, we get 0.886. Well, that's pretty close to 1. That's on the side of that scale close to 1, so that indicates a relatively strong correlation between these 2 quantities. And if we graph those points, we see, yeah, well, it looks like they're following this straight line pattern, or this straight line behavior. When one goes up, the other seems to also go up. So that indicates a relatively strong positive correlation, or a strong positive linear correlation between the x values, the diameter of the trunk, and the y values, the height of the tree. And so basically, the correlation coefficient, and this is really important, this is the essence of the correlation coefficient. It's used to answer a simple yes-no question. Is there a relationship? Yes or no? So again, the word relationship, sorry about that. The word relationship, the word relationship and the word correlation, those are sort of interchangeable. The proper statistical term is correlation. And so if that correlation coefficient, when you calculate that value of R, if it's close to 1, then yes, there's a correlation. Or if it's close to -1, it doesn't matter if it's positive or negative. If it's close to +1 or close to -1, we say yes, there's the correlation. And if not, we say there's no correlation or no relationship. And now this value or this number that sort of separates the answer of yes from the answer of no is called a critical value. And the critical value, it sort of separates the yes range from the no range. So if you calculate the correlation coefficient and it falls in the yes range, either here or here, then you say, yes, there is a statistical relationship between the two sets. Now, the critical values, at least for this course, the critical values come from table A6 in our textbook. And, any statistics textbook you pick up will have a similar table of values. And this is the table of values that determines where that cutoff is between the yes and the no. And it's based off of two things. One, the value of alpha. Now, I don't want to talk about alpha too much because it's a topic for another discussion, but alpha is the significance of the test. And at least in the context of this course, alpha is always given to you. So if you're doing a problem, it will say, is there a statistical correlation? Use alpha equals 0.05 or use alpha equals 0.01. So you have two columns of critical values, one for 0.05 and one for 0.01. It's also dependent on how much data you have. And so N is the number of pairs of data that you have. So let me go back a few slides. We have, in this case, 8 pairs of data. So as soon as you see 8 pairs of data, that tells you that we're in the row corresponding to n equals 8. So it's either your critical values are either going to be 0.707 or 0.834, and that depends on your value of alpha. And again, that's going to be given in the problem. So for example, what are the critical values for 8 pairs of data with a significance of 0.05? Well, 8 pairs of data tells you you're at this row on the table, and alpha equals 0.05 tells you you're on this column. And so it looks like our critical value will be, in this case, 0.707. And that's specifically for 8 pairs of data with alpha equals 0.05. Then your critical values are plus or minus 0.707. So this comes first, right? When you're calculating the correlation coefficient, if it is bigger than the critical value, the answer is yes. There is a relationship. Or I should say, if it's bigger than the positive critical value or smaller than the negative critical value. Either way, yes, there's a statistical relationship. And once you've established the yes, yes, there is a relationship, then you can move on to using that relationship to predict things or estimate things that haven't happened yet. Now, before we talk about that, one important aspect of this that I really want to emphasize is that just because you determine that there is a relationship does not imply it's a cause and effect relationship. It does not imply that an increase in one actually causes an increase in the other, even though it might be obvious. Even though it might be obvious. If you increase the amount of hours you study, you should, in general, increase the grade you get on an exam. Now that seems like there should be an obvious relationship there, but that's not what we're doing here. We're not analyzing a cause and effect relationship. We're just sort of determining whether or not there is a relationship. Once we do that, then we could further study the topic using other methods to determine if it is a cause and effect relationship. For example, if you look back, let's say at the city of Boston, and in the city of Boston, over the last 70 or 80 years, if you look at the price, the average price of a slice of pizza, and you look at the price of one ride on the MBTA, the bus or the subway. Over the last 70 or 80 years, these two quantities have been increasing at about the same rate. The cost of a slice of pizza has been going up. The cost of a ride on the bus or the subway has been going up. And they've been both going up at about the same rate. So there's a relationship there. But it's not a cause and effect relationship. You can't say the prices that pizza shops are charging has caused the Boston MBTA to raise the price of the subway. And you can't say that when the city of Boston raises the price of a ride on the subway, pizza restaurants in turn increase their prices. So one of these is not causing the other one to increase. But they're both increasing at about the same rate. Now, that could be due to some other external factor. Well, and in this case, it's probably due to inflation. Inflation is the general increase in the cost of goods and services. And pizza and the subway both fall under that category of goods and services. So they're both going to increase based on inflation. It's not that one of them is causing the other one to increase. There's no cause and effect there. All right, so this is really important. This is usually how it's stated. Correlation, which is what we're studying, does not imply causality. Now, we're dealing, in this particular topic, we're dealing only with linear relationships. Okay, linear straight line relationships. Just because there's no linear correlation or there's no linear relationship doesn't mean there's not some other relationship. For example, this scatter plot here, there's definitely a pattern that these points are following. They're following this parabola. And so in this case, there is a correlation. It's just not a linear correlation. Would be an example of a quadratic correlation, which is a topic for another day in another class. In this introductory stats course, we're dealing only with linear or straight line patterns, straight line relationships, straight line correlations. Okay. Now let's talk about that second aspect of this, the predicting things that haven't happened yet. And for that, we're going to use what's called a regression line or a regression equation. So once we have a scatter plot, once we have those points plotted and we've noticed the pattern and we've calculated the correlation coefficient and we've determined, yes, it looks like there's a linear relationship. Can we find a model for that relationship? And in mathematics, the word model is synonymous with equation. So can we find an equation that describes that relationship? And that's called a regression equation, and the graph of that is called a regression line. And can we predict the value of one of the variables for some new value that's not part of our data set, some new value of the other variable? And then we can look also into what part of the variability in those two sets is associated. Well, what part of the variability of the response variable is associated with variation within the explanatory variable? And that line that we're looking for, I remember the equation of a line, y equals mx plus b. So that line that will best fit the data is based on, so now remember, with a scatter plot, normally your points are not going to follow a perfect straight line. So let's say here's 5 points. So that line is going to be the line that is as close as possible to those points. So you see, each of these 5 points is not on the line. There's some error there. So there's a little bit of error with that first. This point is a little bit above the line. This point is a little bit below the line. This one's below, and this one's above. So the line we're looking for, this y equals mx plus b, is the line that has the smallest possible error between all of the points on your scatter plot and the line itself. Okay. And so we'll let d be the vertical distance, and that's the error. The vertical distance between the point and the line. So there's one value of d, there's a little value of d, there's a value of d, that's another d, that's another d, that's another d, and that's another d. And so we're not going to look at the values of d because some are positive and some are negative. So we don't want the positives and the negatives to cancel each other out. Because if one point has a error of +3 above the line by 3, and if another point has a value of -3, well, +3 and -3, when you add them up, you get 0. So we don't want things canceling out. So we're not going to use the values of d. We're going to use the values of d squared. Because if you take a positive number and you square it, you get a positive number. And if you take a negative number and you square it, you also get a positive number. So we're going to look at the squared values. So we want the sum of the squared distances to be as small as possible. So there's a lot of different lines. There could be a line here, a line here, a line here. One of those lines will have the smallest total error, and that error is given by the sum of the squares. So this regression line is also called the least squares line, or the least squares regression line. And that's because we're looking at the squares of the distances between each point and the line. And so in statistics, in algebra, if you've taken an algebra class, and I'm assuming you have because every student in this country has to take algebra in high school, I'm assuming you're somewhat at least familiar, at least it sounds familiar, this y equals mx plus b. And if we want, we could say y equals b plus mx. Same thing. 2x plus 3 and 3x plus 2, 2x plus 3 is the same as 3 plus 2x. The order doesn't matter. But in statistics, so this is not algebra, in statistics, the y-intercept, we give it the symbol b0, and the slope, we give it the symbol b1. But that's it's just the same old y equals mx plus b that you're familiar with. There's a slope and a y-intercept. Now, As with the correlation coefficient, calculating these things by hand, and when I say by hand, I mean paper and pencil and a calculator. Even with a $150 graphing calculator, these things are very cumbersome, very time consuming, very complicated to calculate. So here's your formula for the slope. So it looks about as complicated as the formula for correlation coefficient. And here's your formula for the y-intercept. These are not things you want to do by hand. Right? My advice, use Excel. And I show you how to do this in my next video. So on the last slide, there's one more slide to go. On the last slide, we have an example of a problem. And I have another video where I work through this problem on Excel and show you how it's very quick and very easy to calculate these things on Excel. So you would think there's probably a relationship between the size of a house that's being sold and the price. Not 100% of the time, not always, but if you look at 100 houses or 1,000 houses, you would see a trend probably where bigger houses sell for more money. So here's an example of 8 houses. So n equals, let's say n equals 8. So here's 8 houses, and for each house, you have a pair of values: the size of the house and the selling price. Okay, so what I want to do is use alpha equals 0.05 for the critical values. I want to go through the whole process. Calculate the correlation coefficient. Determine if there is a relationship using the critical values. Once we determine there is, then come up with a regression equation, that y equals mx plus b, or the predictor equation that can be used to predict something that hasn't happened yet. For example, what would be the selling price of a house? Well, this hasn't happened yet, but what would be the selling price if the house was 3,500 square feet? So based on the stuff that has already happened, can we predict something that hasn't happened yet? Okay. And that is the topic of my next video. If you have the PowerPoint file that I've been going through, if you click on this link right here, it will take you to a video solution of this particular problem where I go through every step that I've explained in this video. All right, so that does it for just this general introduction to correlation coefficients and linear regression equations.